Tēnā koutou katoa. Ko opuke te maunga, ko otakaro te awa, no o tautahi ahau. Ko von Hertebroekes toku whānau, ko Jack toku ingoa, no reira, tēnā koutou katoa. Hi everyone, my name is Jack. I'm a software engineer from the University of Canterbury, and at the beginning of this year, I, under the supervision of Dr. Richard Green, worked on developing a method of autonomously detecting facial tics in video recordings. Tics are typically defined as an abrupt and involuntary movement or sound, with facial tics being a subclass of tics that involve the muscles in the face. Involuntary tics can be an indicator of a number of disorders, such as Tourette's syndrome, transitive tic disorder, chronic tic disorder, etc. When medical professionals work to understand facial tics in patients for the purpose of diagnosis, they consider a number of factors, including the frequency of facial tics and the characteristics such as which areas of the face are involved in those tics, which muscles are stimulated. As someone who has been diagnosed with chronic tic disorder and as a software engineer, this was a problem I was particularly interested in applying computer vision to. With this work, we aim to understand whether information about facial tics can be extracted from video recordings without a medical professional needing to manually review the entire video. Essentially, we wanted to identify facial tics within video and to be able to provide information about the movement of each facial feature. The facial features that we chose to observe were the mouth, the eyes, and the eyebrows. We considered observing the nose, but the skin at the top of the philtrum and at the bridge of the nose are quite close to cartilage, so they don't move that much when a facial tic is happening. Also, other facial features may move, which we could observe in lieu of being able to detect nasal tics. So only one existing solution was identified for this problem regarding the detection of facial tics. This was proposed by Laville. Laville's method only detected facial tics using the mouth, and it only provided a binary classification. So whether a tic was happening or not, it did not provide detailed information on the characteristics of that movement. For example, how much the mouth moved by or for how long. Emotion recognition was also reviewed because this is a similar research area. It involves movement of the face and detecting what that means. So Little wrote a paper that used machine learning to classify various facial expressions. However, this classification was poor in the neutral position, which is quite an important position to be able to identify if you're looking for facial tics. And there was, again, no information provided on the movement characteristics, so how far each feature moved. The method we are proposing addresses the issues of previous work by including information about the characteristics of each facial tic in the form of graphs. Our method is comprised of 4 key stages, which I will describe now. Firstly, we needed to detect the position of the face within the video. To find a bounding box for the location of the face, we used a histogram of oriented gradients with a linear SVM. We then used a cascade regression algorithm to position 68 landmarks within the face. The landmarks that we used were taken from the iBug 300 Faces in the Wild challenge, and the landmarks are shown on this slide on the right. Secondly, we needed to split the face up into the facial features of interest, so the eyes, the eyebrows, and the mouth. We defined each feature based on the positions of the landmarks that formed its convex hull. and we represented the center position of each facial feature using a coordinate system that was based on the line from the bridge of the nose to the chin. We were then able to extract the position and area of each facial feature and use it for tic detections. To estimate the neutral position and the area of each facial feature, we took a rolling average of the feature's position and area over a period of time. We then detected deviations from the neutral position, and large deviations that returned to neutral after a short period of time were considered to be facial tics. Here we see an example of the information generated by the proposed method. The graphical data for each facial feature is visible at the top, and the timeline of tic detections in the video is shown at the bottom. The method has a number of configurable parameters, some that are configured globally and some that can be configured on a per facial feature basis. For the rolling average used to calculate the neutral positions of facial features, a window size must be defined. The area and position data of each facial feature is also smoothed using Gaussian smoothing, which requires a window size and a standard deviation to be defined. Parameters must also be configured to ensure that long duration facial movements, such as smiling, that are not synonymous with facial tics, are not detected as facial tics. For this, a window size and a threshold is required. Finally, movement thresholds must be configured for each facial feature individually to stop minor movements such as blinking or breathing from being detected as tics. These parameters are based on pixel distances and frame rates, so must be configured differently for different experimental setups. Our method requires the face to be well lit, facing the camera, and to spend most of its time in a neutral position. There is a lack of publicly available video that fits these requirements, so we recorded our own. The tics that were recorded are based on my own tics, which provides a level of authenticity. In total, we recorded 50 facial movements, with most of them being tics, and with some of them being non-tic movements, such as smiling, that were used to evaluate the false positive rate of the proposed method. The first 30 recordings were used to set up the parameters used in the proposed method. We then used the remaining 20 videos for the assessment of the method. We found that all 17 facial tics present in the videos were detected, and that no tics were falsely detected when the face was in a neutral position. However, the method did have some false positives for non-tic movements, such as smiling. In conclusion, we managed to improve on the method proposed by Leveal by including information on movement characteristics and by including other facial features in the data provided by our method. We also achieved a much lower false positive rate for neutral expressions than we would have been able to achieve if we had attempted to adapt Little's method for emotional detection to a facial tic detection context. The graphical information provided by the method contains information on the characteristics of each facial tic, and the timeline at the bottom can be used to highlight the time at which each tic occurred. Future work on this method that we've proposed might involve adding new facial features, making configuration of the method's parameters automatic, or assessing the usefulness of the method in a real clinical setting. We hope that this research can inspire future work that helps reduce the cost of diagnosis for tic disorders. This brings us to the end of the presentation. I would like to thank you all for listening. Thanks again to Richard Green for supervising the project. If you have any questions that we aren't able to answer at the conference, please contact me or Richard at the email addresses provided on screen. Otherwise, I hope you all enjoy the remainder of the conference. Tēnā koutou katoa.